y'all, and welcome to another high-powered episode of the High Voltage Live Show. I'm your host, Willie Snyder with Nat King Code, joined by Mr. James Stallcup of the Volt Online Academy and creator of the High Voltage Live podcast. And we're very happy to have you guys all in the audience. We've had a lot of great participation. We hit 28.5 thousand on our NEC for Dummies group, which is really awesome. It's been growing fast. We really appreciate everyone participating in the code question of the week, the myth of the week. It's been awesome. Like, that group's just been participating more than any other group, and it's really awesome. It's really a joy. And I just have a lot of fun doing them. Looks like we have already Mr. David Engelhardt in the house.
Mr. Engelhardt.
Welcome in, sir. Thanks for joining us tonight. And so it's really awesome that I'm able to kind of go through, think of what we're going to do, and just kind of come up with a crafty way to add it to the myths on our, we got Mr. Mike Wilson. What's up, sir?
Hey,
welcome in, brother. But it's really fun to think of like little crafty ways to, put these together. And looks like we have the IAEI in the house, Mr. Gibbs. Thanks for joining, sir. Appreciate you jumping on in. We're just really honored to have so many people participate. I hit like 10,000 again, or I hit 100,000 this time, and it's just crazy. Like, I'm hitting 60,000 every week, and it just means a lot. Everyone's like checking them out and just kind of getting involved. And sometimes I try to throw the picture in a little weird, or try to throw different things in to kind of make you guys read the question, kind of think about what's going on really. And a lot of guys are like, oh, well, you just said this and you should have said this or whatever. And I do try to edit them and change them around a little if I get the wording off or whatever, and like I say, I'm not a code instructor. I'm just a journeyman in Colorado. You know what I mean? I'm just doing this for fun, and it's not like I'm trying to say I'm not wrong sometimes. You know what I mean? I make mistakes too, but it's a lot of fun. And like I say, there's a lot of guys at the job site that's like, yeah, I didn't think you could share neutrals anymore. I'm like, okay, we're gonna have to do this. And then James's topic tonight actually was pretty awesome. That I think a lot of guys are gonna learn from it. I mean, it's confusing. A lot of people think you got to size off the 75-degree C chart and stuff like that. So I think James is going to kind of open everyone's eyes on that. And I wanted to say, may the 4th be with you, everyone, and happy Star Wars Day.
And that brings you to the meme of the week.
There you go. Yeah, and it was funny. I actually got a Facebook ban for that. I don't know what happened. I don't know what it is. Like, maybe it's a copyright thing. I don't know. But I tried to post it, and they're like, either delete this or you're going to jail or whatever. And I was like, man, there's nothing wrong with this. I don't know what's going on. But so what I did was I tried to make a different one. And I went and I just got a random picture of that same shot of the Death Star. And then I was like, never forget 5/4/1983, because that's when the other Death Star blew up. And they freaking banned that one too. So there must be something flagged with that image or something. But I was like, oh, all right, whatever. I was like, I guess I can't post it on my group or wherever, but it was pretty funny. I was just messing around.
The Death Star.
Yeah, but no, there's a lot of cool Star Wars stuff out there. I actually did a Willie Jackerson experiment podcast on May the 4th be with you last year. So if you guys want to check it out, it's on Spotify and it's on like 7 different platforms. But it's pretty funny. Just doing a bunch of Star Wars music and of course some metal.
I was actually the other night. I was just got home. It was late. I was chilling. I was working on some stuff, and I was like, I'm gonna turn on something, and I watch one as a spinoff. It's called Star Farce. It was actually pretty funny. I was like, really? I never even knew that was there. It's called Star and Farce, Farce. And they'd say, "May the farce be with you."
Okay.
It's sort of like Blazing Saddles or something like that. It was
Okay.
funny as hell.
Kind of a cheesy. Yeah.
Yeah, I like
We
those
mess around.
movies.
We mess around with that a lot.
All right, you ready
So,
for your myth of the week?
do the myth.
All right.
It's time for Myth of the Week.
All right, so this is a really interesting myth that we came across this week. There's a lot of people out there that say you can't share neutrals anymore, and we kind of ran in. This is actually just a funny picture I stole from NEC Live. The boys over at NEC Live will do posts. Dean and Corey will do posts over there where you're the inspector and you bust them on different code violations. And yes, this is a code violation. I believe it was 408, 408.41, I believe, is the actual code violation, where basically one terminal per grounded conductor. I think that I did do some research on this, and I do believe that the ground in conductors are permitted to do up to 3 conductors per terminal on the ground in conductor. The grounded conductors per 408.41, I believe, are only permitted to use 1 per terminal. But that really wasn't what the myth was about. The myth was about sharing neutrals, and so I did like the true or false on there. I did try to throw the 2020 code in there because a lot of people think that under new code you can't share neutrals anymore, that you need to run a dedicated neutral for every ungrounded conductor. And so basically this myth is busted. This is a myth, and you can share neutrals with 3 ungrounded conductors of opposing phases as long as all 3 phases are simultaneously disconnected. So myth busted. One of the things that I ran into, and this is on one of the jobs I was on, they have modular furniture. Well, the modular furniture still shares neutrals. So we were instructed on the engineered print to pull dedicated neutrals all the way out to that equipment, and it didn't matter, because since that and yeah, Mike makes a good point too. Emergency circuits, say you can't use a multi-wire branch circuit. We're gonna have to tie that in with one of our myths, because I don't 100% agree with that interpretation that it just cannot be done. We did a job, and I went over it with the inspector, and I had a multi-wire branch circuit that was doing all emergency lighting. And since they were all battery power and it was handle tied, the inspector permitted me to do it. So if you had circuit 2 trip, it would kick the emergency lights on across the whole multi-wire branch circuit. So there wouldn't be any of those phases. So like if you had a set of lighting that was on circuit 2, set of lighting that was on circuit 4, and a set of lighting that was on circuit 6, even though it was a multi-wire branch circuit, if any of those circuits tripped, it would kick on the emergency lights. So yeah, and yeah, I agree with you, Mike. Yeah, for generator backup, yeah, I agree. 719, I believe, says no multi-wire branch circuits. But it's just one of those things that we do. It's a kind of a common practice, and a lot of guys are getting away from it just because it's easier to just especially in like specs, like in our hospital specs, we have to pull dedicated neutrals for everything. But what we ended up doing was we had this modular furniture, and we pulled dedicated neutrals to everything. And what ended up happening was when the inspector come to inspect it, even though we had dedicated neutrals out to the equipment, since it was sharing neutrals inside the modular furniture, we still had to breaker tie it. So that was one of the things I realized, that why this is kind of one of those myths where it's like, you might want to know your rules on this so that if you do run into that situation, you can just, show your boss like, hey, might as well just share the neutral, make a multi-wire branch circuit, put on a 3-pole, because we're gonna have to handle tie it anyway once we get over there.
Sure. Well, you know me, I don't stop at just that point. So
Right.
I'm going to discuss a couple of things here. I went back and looked at everything that I have on my computer that I keep. I go all the way back to 1996 on our illustration. So when you actually get in and you look at 210.4C, where you actually get into your line to neutral loads for your multi-wire branch circuits, I went in and I was looking at that, and
seems like David might be a little ahead of you on the code change there.
2005 to multi-wire to common same yoke. That he's talking about the receptacle. I'm not getting into that. This was specifically here at 210.4C. Now, where they did start making changes is actually in 210.4D, where we get into the grouping, and I'm going to talk about that here in just a second. But as far as 210.4C, it was before 1996, and I didn't have the illustration to put in there, so I was like, you know what, I ain't got time to go back and find all the illustrations, because they're in such older files. For me to grab that, it was in a much older program, and basically I'd have to redraw it. Basically, is what would happen. I didn't have time to do that. Now, when you look at this and you look at 210.4A is where I'm going to start this. It's just your general requirements. And what it says is that branch circuits recognized by this article shall be permitted as multi-wire circuits. I'm just going to stop right there. That we can do that. Then when you get down to C, you pick up the line to neutral loads. And actually, I even would look at this where I'd say, let's look at exception 2, because it'll tell you a multi-wire branch circuit shall be permitted to supply line-to-line loads if all ungrounded conductors of the multi-wire branch circuit are opened simultaneously by the branch circuit overcurrent device. Now that's where it comes in, and we started looking at this where we have these line to neutral loads. Okay.
Right.
And then what they did is people, I remember when this first come out, and when we were looking at this as an example, is where I would go and I had a nonlinear load, let's say, and they come in and
good evening, welcome.
Good evening.
Thanks for joining.
They had these ballasts that they were going and changing out, and they were retrofit and everything, and they were these electronic type ballasts. Well, anyway, you started getting, your leakage current across there. And of course, that's leaking back across where? The neutral. Okay.
Yep.
So you started building these loads up. And when I was coming through, we would take and run 3 hots and a neutral. Okay. And that neutral was good for those 3 hots. Well, now you take those 3 circuits and you started getting all that load on that neutral. All of a sudden, we started having a problem with that, because it was nothing uncommon for us to go over, turn the switch off, and go in there and work on that ballast. And you'd be fine touching that neutral, except for when you touch that neutral and you touch the side of that fixture, guess what? You're the closest point to ground at that point, right?
Oh, yeah.
So that's where the problem come in. And then they started looking at these multi-wire circuits, and where you were switching the neutral simultaneously because of those 3 circuits coming over there sharing that neutral. That's a good example when it first started, what you would see. All right.
Right.
Now, once all that happened, they come in and then they started working. They did it for like 2-3 cycles, but they started talking about the ungrounded and grounded circuits. And and they talked about these where they were for each multi-wire branch circuit, and then they told you that they had to be grouped in accordance with 200.4b. Okay.
Okay.
Now, this is where you started seeing some stuff take place, because when you go to 200.4b, and when you get to Article 200, what does Article 200 deal with? It deals with your grounded conductors, right?
Yes, sir.
And it tells you where you had more than one neutral associated with different circuits in an enclosure, grounded circuit conductors of each circuit had to be what? Identified and grouped to correspond with the ungrounded circuit conductors. And we did this by using wire markers, cable ties, or other similar means in at least one location within the enclosure. So
Right.
they started requiring after that you were sharing these neutrals. Now all of a sudden, since you had these multiple circuits for that neutral, and you may had an older installation and had all these circuits going out for lighting, whatever it was going to. Now all of a sudden, you may have a couple of different neutrals in there that are sharing multiple circuits. So
Right.
now,
And the thing that's funny about this is I've actually seen guys go through and identify them when you have MC cable, and that's not required, because if you look at that language right there, it says that make unique to the circuit that makes the grouping obvious. So if it's an MC cable coming in there, it's obvious that they're grouped together. You don't need to group those again. You don't need to identify them twice.
That's right. And you could have a home run going out there with multiple circuits. You know, you could have 9 circuits and 3 neutrals and 1 equipment ground. Now you got to group those because they're all sharing that one neutral because it has nonlinear type loads on it. You're maybe going out feeding a whole lot of computers and things like that, and all of a sudden you're putting load across that neutral. So that's why these neutrals were being shared, and now they want to have a mark because you could have multiple in there. Okay.
Yeah, welcome in, Andrew. And that's
Hey,
a good point, because some guys like to do it, and I wouldn't doubt anybody. I wouldn't, doubt anybody for like, I'm a big label guy. I like labeling. I'll label it, even if it's labeled. I'll label it twice. I don't care.
Right. Now, the other part of that 210.4, and I say this at the end of it, because that's where you get into the disconnecting means. And it tells you each multi-wire branch circuit shall be provided with a means that simultaneously disconnects all ungrounded conductors at the point where the branch circuit originates. Okay.
Right.
And then there's an informational note, and it tells you to go see 240.15B, but it's B1 you're going to look at. And it says you can do this by using what? Identified handle ties, that is permitted as a protection for each ungrounded conductor for that multi-wire branch circuit, where it only serves what? Single phase, line to neutral loads. And if I go back here and I'll look at 210.4C, what does the heading say? Line to neutral loads. So that ties everything in, so you know exactly the rules. And these are all the rules I would look at when I'm applying, where I'm going to be simultaneously switching that in the neutrals being shared.
Yeah, and David Englehart needs to get that breaker tie in there, because it looks like he's getting zapped on the 3-phase multi-wire branch circuit. Learned it the hard way, sir.
David, that happened to me when I was younger. It did. I know exactly what David's talking about. I got popped, and I was like, God dang it.
Yeah, and I've seen that too, Andrew. We were doing a job where they were using it was called 1222, and I never even seen that before, but it was like you had a 12-2 Romex with a black and a black neutral marked, and then you had a red and a red neutral marked in the same cable with the ground, with a bare ground. And it was Romex. It was pretty crazy.
Well, I think for that myth of the week, I think that all them sections completely tie in everything you need to look at as far as simultaneously disconnecting all those ungrounded phase conductors with a shared neutral.
Yeah, and it brings up some other myths that we might want to go into, because a lot of guys say you can just put a piece of copper through the holes of that breaker and handle tie it, and That's a real big debate to me, I mean, it's all right if you don't have. And then the other one we ran across, James, that I think you'll have fun with this one is which circuits are required to have common trip. Because I know a lot of times if you have a 3-phase load and you don't have a common trip, then you could have that. If it's like a motor load, you could have that single phase, the motor, and actually do damage and stuff. So
sure, I'll cover that. Whatever mess you want to go through, I like going through everything. And
yeah, Andrew knows what I'm talking about.
That's taking a solid copper and taking it through the handles. I've seen that too.
Yeah.
The nail is the best handle type. Seen that too.
And they work. I usually use a 632 with a nut on there. Seems to work okay.
All right, ready for my topic?
Yeah, let's do it.
Looking forward to this one. All right, here we go.
Hey, real quick before we get started, James.
All right.
We had a big pot stir just roll in. Old Mark Candles, and he come to stir the pot. Is a motor and outlet.
No. No. Matter of fact, Mark's going to be on next week.
All right. Yeah.
I'm going to give him a call. What day was I calling you? Sunday. Because I'm playing golf Saturday. So, and he's in class today and tomorrow. So I told him I'd give him a call Sunday and we'll set up what he's going to do and everything. But once again, thank you, Mark. We always appreciate you being on, brother.
Yes, sir. Agreed.
Okay. Now, what I'm going to talk about, and this is going to deal with the adjustment and correction factors as it relates to the temperature rating of the conductor as far as derating is concerned. And, I remember when we were doing this has been many, many, many years ago. I'd say 20, 25 years ago. And I'm not going to tell where I was at, but I was doing a course and they had 2 engineers in there and apparently they designed it wrong. And the electricians were arguing with them, telling them, no, that isn't right. And basically they had to do some derating and they were trying to do something else. And I took them through the sections of the code and they said, well, I don't agree with what that says. And they got all upset and they actually went out and told the moderator that I was a terrible instructor, blah, blah, blah. And said a bunch of stuff. And then I came out at break and she goes, what's going on? What'd you do? And I was telling her, basically what happened. And there were 2 guys standing there and they come over and they said, no, they said what he said is exactly right. And they designed it wrong. And now they're bashing on him because he didn't agree with them. So, but everything that I usually do when it comes to discussing code and stuff is to take you through and show you the language. And then from that point, you can make your decision. I'm going to give you my opinion of what I think it means. Okay.
Okay.
So when I start this off, the first place
that's the first time. That's the first time ever you're giving your opinion, just for everyone out there.
Of course. But when I look at this, I'm going to tell you right away that the first place you're going to start is at terminations. Okay. Because the terminations are going to matter. And most of the terminations you're going to be dealing with are 60 and 75 degrees C. Okay.
Right.
And then it becomes part of what is the conductor rated as in relationship to that termination. Okay.
Right.
So when I go over, I'm going to look at 110.14C to start this off. Now, when you look at this is where you get into your electrical connections, and it talks about temperature limitations. And what it says here is the temperature rating associated with the ampacity of a conductor shall be selected and coordinated so as not to exceed the lowest temperature rating of any connected termination, conductor, or device. And that's why I said most everything you're hooking to and at the panel, your equipment stuff is going to be 60, 75 degrees C. Now,
Yes, sir.
the next sentence here is the most important. It says conductors with temperature ratings higher than specified for termination shall be permitted to be used for adjustment, correction, or both. So it's telling
Nice.
me right here that a conductor can have a higher temperature rating. And this is where we're going to get in and we're going to look at a 90-degree C conductor and a 75-degree C conductor. Now,
Okay.
what I'm going to tell you at this point is this. You're going to need to look at table 310.4, okay?
Yep.
And there now in the 2023, it used to be A. I think now it's Pren 1 and Pren 2. But when you go over here and you look at this, this is a good example. I had to condense the table to get the information because it's a pretty big table. But if you look at this table, this is your conductor application and insulations rated 600 volts. And if you come and look at the last column I'm dealing with there, it talks about heat resistant thermoplastic, which is THHN. And THHN can be used in dry and damp locations. If I'm outside, I'm going to have a THWN conductor, and we'll look at that in just a minute. But in this case, if I have THHN, you'll see the maximum operating temperature for that conductor is 9 degrees C.
Yes,
Okay?
sir.
Now, if I come over after that and I look at table 310.16, now this gets interesting because if you look at and you can look at the amperages here and everything, but I want you to look at the heading of this table. It says ampacities of insulated conductors with not more than what? 3.
3.
That's right. And it says in a raceway cable or earth directly buried. Okay. Now, if I look over there as an example, let's say I have a number 12 THHN. I come across, it tells you it's good for 30 amps. But now, if you look in the 75-degree C column, looky there. Do you see THHN there? No, you see THWN.
Right.
If you come down and pick that up, now you're going to derate at 25 amps. Do you see that?
Yep.
If I look in the 90-degree C column, looky there, I see THHN. That's good for 30 amps. A lot of people look at those conductor tops. They never pay attention to what's up at the top of the table. There's a reason that those are there, and that's for derating purposes because that's what the conductor's rated at. But if I'm going to size, once I calculate my load and I've got 75-degree C terminations at the panel and the equipment, I'm going to use the 75-degree C column for my amperages. Do you see that?
Yeah, and that's kind of what Andrew's question is too, you know. So are the main lugs different than landing on a breaker? Can you use the 90C column to size your wire landed underneath the lugs?
Sure you can. And that's what I was just saying. I already knew that question was going to come. That's why I went ahead and put this in order.
Right.
But I want to point out, because a lot of people don't pay attention to this. This is the rating of the conductor, what its temperature rating is. Okay. And that's why they're under certain columns there. Then when I size a load, it's based on what? The terminations. Once you calculate that load, what are your terminations? So in other words, if I'm at a panel board and I've got a 60-degree C termination and I'm going to a 75-degree C piece of equipment, I'm going to use the 60-degree C column. Okay.
Yeah, good point. Good point, Mike.
Yeah. Now, if I take and I've got a 65/75-degree C rated breaker and a 75-degree C termination at the equipment, I can use the 75-degree C. You see that? Okay. And that's why I wanted to start this off by pay attention to the termination. Then we look at what the temperature rating is of the wire, And that's when it determines what I can use as far as derating for the adjustment and correction factor is concerned. Okay.
Right. And where this kind of came out was I was basically talking to a guy and I was like, yeah, if you put 3 boats of number 10 in a 1-inch, then you're derating at 50%. You're going up to 90-degree C column. Your conductor is still good for 20 amps if you use number 10.
Right. Now, look at this. This is temperature rating, and it tells you this temperature rating that's in table 310.15B11 shall be used with which tables? Table 310.16 and table 310.17. That's the note below the table. Well, in this case, we're just using table 310.16. And let's say I have an ambient temperature of 100 degrees and I'm using THHN, I can come across it in that 90-degree C column, my derating factor is 91%. Okay?
Right.
Just as an example. Now, when I come over here and I look at table 310.15C1 and say I had 8 current carrying conductors, that'd be in the area for number of conductors 7 to 9. I come across, it has a 70% derating factor there. Okay? Right. Now, the next thing I want to point out here is below that table, there's a uppercase A, and it says the number of conductors is the number of conductors in the race wear cable, including spare conductors. This count shall be adjusted in accordance with 310.15 E and F. The count does not include conductors that are connected to electrical components that cannot be simultaneously energized. Now, let me explain. When they're talking about that 310.15 E and F, what they're getting into is, say I have a neutral conductor. If I have a neutral conductor that carries the major portion thereof, which would be in what we say is 51% or more, then that becomes a current carrying conductor also. Okay.
Yeah, and also what they're talking about too is I've seen before where they have like a momentary contact switch, and 50% of the time the load's on, say, A phase, and then once it hits a certain point, it clicks over to B phase. Then those conductors are not simultaneously energized. You're not carrying load on A phase and B phase. It's carrying 20 amps on A phase, and then it clicks over and it's carrying 20 amps on B phase. And that's a mechanical switch that changes the load.
That's
so
right.
Basically, there's no way that load could be on A and B at the same time. It's only going to be on A, or it's only going to be on B at any given time, regardless how you change the controller.
Right. And people will say, what is considered current carrying? That's anything that operates for 3 hours or more. Okay? That's current carrying.
Now, there's a big thing that I learned that you have to always carry with that is it has to run at maximum current for 3 hours or more. So, like if you have a piece of equipment that, like good examples, like a refrigerator. A lot of people think a refrigerator is a continuous load, but a refrigerator does not run at full load for 3 hours or more.
No, it cycles.
Yep.
Now, I will say this. There's one other thing that I will point out. There's also, which I actually put it in this presentation, we're going to look at Annex B, and we're going to talk about also when I'm doing these calculations where you can take and have these current carrying conductors in the raceway and then other conductors that are not current carrying. Okay?
Right.
So we're going to get into that also, and I'm going to show you the calculations. There's 2 of them that I'll look at there when I'm applying for that calculation. And I've seen a lot of courses online. I've never seen anybody go through and cover that portion of it. I've seen where they'll cover portions like this, but I don't think they go quite as in depth as what I'm going to do. But it'll make it to where you have a different thought process in the way that you look at adjustment and correction factors. Okay.
Hey, we should rename this show like Steel Stallcup's Knowledge or something like that.
Nah, I like how
that's awesome, dude. You're doing a great job for us, brother.
Okay. Now, when I look at this, this is what anybody that's prepping for their journeyman, these are going to be the new illustrations. I mean, I think they look awesome. But on the left-hand side, when this comes out, there's actually going to be an NEC loop that's going to take you down through this. And you click that to go get your information so you can follow along with what I'm going to tell you. Now,
Right.
as I look at this in step one, there will be a calculation ahead of this that we actually have the sections and tables and everything you're going to look at. But when you get to the exercise problem, we don't put the sections there because we want you to sort of start learning at this point where to find the information. Okay.
Right.
So, but since we're doing this, I'm going to tell you where everything is. Now, in step one of the exercise problem, we have find an amperage of conductor. You're going to go to table 310.16. Now, you'll see in our known values there, we're going to tell you that we have a number 12, THHN copper. Okay. Now, if it's THHN, we've already looked at table 310.4 and it's 0.4 prin 1. It's going to tell you I can use a 90 C column for THHN. So I look at table 310.16, the 90 C come across, it's going to tell me it's good for 30 amps. Right. Then I'm going to look at finding the adjustment factors. And I'll actually go back so everybody can look at this. So we have 4 current carrying conductors. I come back, look at 310.15 C1, and from 4 to 6 conductors, it tells me I can take it at what? 80%. Okay. So I'll go to my step 3, do the 30 amps times 80, and that's going to limit the ampacity for each one of those conductors to 24 amps. That's a pretty easy calculation as long as you know the information and where to get it.
Hey, you know what else you could use in that illustration?
You
could use the conduit as ground. You don't show ground in that there. And that's good. A lot of people need to know that you don't need to pull a ground through every piece of EMT per 250, 118.
No, you don't. But the reason we did it like this, because we're mainly trying to show what are the current carrying conductors here. So if you look in this in the neutral, in this case, if I look at 310.15E, I'm saying it's a major portion of, so we're just telling you the neutral's current carrying at this point. Okay.
I agree.
So I would have to count that. All right. Nice. Now, if you look at the next one, this is where you're going to get into the temperature rating, and you're going to be looking at 310.15 B11. Okay. So if I look at this, I have THHN. It's copper. I go over to table 310.16. I know I can use the 90 C column. I come down. It tells you number 8's good for 55 amps. Now, the next one, when I go over and I look at table 310.15 B11, it'll tell you at 125 degrees Fahrenheit, I can have a derating factor there of 76%. So all I'm going to do is take the 55 amps times 76%, and that's going to give you an ampacity that's limited for each one of those conductors at 41.8 amps. Now, so far, these are all very simple calculations that you know how to use the conductor now and where to get the information.
Right. And Andrew, so it's 250, 118, but basically in 250, 118, there's a list of acceptable equipment ground conductors. And one of those in the list, and I believe it's in list number 6 or something, and the list item is EMT, and EMT is acceptable to use as an equipment ground. The only problem is it's only acceptable as long as you tighten all the set screws. So I have a really funny story. One of these podcasts, I'll have to pop it out. I think me and James did it on the Willie Jackerson experiment. Maybe I'll send you a link, Andrew. It was pretty funny. But David has a good point that the equipment ground would affect the conduit bill if you were doing that for part of the illustration.
Oh,
so
sure.
Very good point. Very good point, David.
All we're doing right here is just giving you an example of current carrying conductors. But I will say this, and I want to address one point that was asked there. When you start looking at the equipment ground, I'm gonna make a hypothetical here. Let's say that I've got these derating factors and I apply an adjustment and correction factor, and all of a sudden the conductor is not large enough to go over and feed that load. Now I've increased the conductor size for the ungrounded phase conductor, right?
Yep.
Okay. Now, when you get in to looking at that, I could also be looking at this and I could be looking at a voltage drop. Okay. That can also increase that conductor size. Well, I'll make up a problem here for you. Let's hypothetically, I don't have the table here, so I'll be guessing at the exact values. But let's say that I have a panel board here and I go over and I feed, we'll say another panel board, I'm setting up a load. And let's say over here that main breaker over there is 175 amps of load I'm going to be feeding. Now, what'll happen is due to voltage drop, and your voltage drop calculation that I would use in this case is 2 times R times L times I divided by 1,000. So 2 is your constant. Then you're going to go to chapter 9, table 8, and you're going to get the resistance of the conductor, and we'll just say it's uncoded. And you'll go over and get that. Then you got the length of the conductor and the amperage. Okay, you got all those values, divide it by 1,000, and you do your voltage drop. Now, let's say I do that calculation and I had to increase that ungrounded phase conductor one size. Okay, now, if I go over there, I know I need a 2-aught to go over there for that 175 amps, because if you go look at table 310.16 for 75 to 75 degree C terminals, it's going to tell you that's good for 175 amps. So I go up to the next size due to voltage drop. It fits within the parameters and all that. And I need a 3-aught conductor, which is good for 200 amps. Now, I've gone up in the sizes there. Now, if you go over and you look at 250.122B, that's for your equipment grounding conductor. And I'm not going to do the neutral. I'll do it in another podcast because that's over in 240.22.
I was like totally lost up there you're talking about when I was sitting there looking at this. I'm like, man, where's that 3-aught at? I can't find it. I'm like totally lost.
No, I'm just making something up here. So what
you should go back to the screen. Like you should go like take that illustration down or something.
Well, think of this. If I go over and look at 251.22B, it's going to tell you when you're doing this calculation, it'll be based on the circular mill. So you may have, you're going to increase the size of that equipment grounding conductor going over, which like David was saying a while ago, this could change the conduit fill. Okay. Right. So you may have to make the conduit a little bit larger. So
I totally agree, Andrew, but he had me lost on that one. I'm sitting there trying to find the 3-aught on there.
I told you it was an example problem I'm making up off the top of my head. So
you got to take the illustration down and put it on something different. Then
I know.
Then we can use the imagination.
So what you would take here is you would take what you'd go to chapter 9, table 8, and you would get the circular mill of that 3-aught conductor. Then you'd get the circular mill, the 2-aught conductor, and you're going to take that 2-aught conductor circular mill and you're going to divide it into the circular mill of that 3-aught. And when you do that, it's going to come out to like 1.268753, something like that. Now, you get your multiplier. Then you're going to look at what if I look at the breaker and I go over and I look at table 250.122, it's going to tell you for a 175 amp overcurrent device, you need a number 6 equipment ground. Now, you're going to go over, since you know it's a number 6, and you're going to go look at chapter 9, table 8, and get that circular mill. And I think it's something like 36,340, something like that. Then you're going to take that and you're going to take that multiplier. And once you multiply it, you're going to come up to somewhere around 44,250, something like that. Once you get that new circular mill value, then you're going to look over in chapter 9, table 8, and you're going to look at the circular mill for each conductor, and it's going to tell you need to take that that equipment ground up to a number 4 now. Okay.
Okay.
These
All
are
right.
things, and I'll do a podcast where I can show all this. But since he brought it up and he's looking at equipment ground stuff, there's things you have to look at that go further than this, because now you're getting into these derating factors and stuff. Okay.
Right. I
Now,
agree.
Now let's look at this here. This is where I'm going to apply. We're on the illustration on the slide now.
Okay. All right. I'm not looking for 3-aught anymore. About 10 minutes ago, I quit looking for 3-aught.
I love it. Okay. Now, this is the same calculation. The only thing I'm doing here different is I've got 8 conductors, and we looked a while ago at 8 conductors. It was a 70% derating factor, and I actually set 100 degrees earlier, and I would look at 310.15 B11. For 100 degrees Fahrenheit, I'll take it at 91%. So you'll just take the 30 amps for that number 12, THHN, in the 90 degree C column, and multiply it by 70 and 91%, and that'll give you a limited ampacity for each one of those conductors of 19.11 amps. Now,
Okay.
so far, just looking at everything that's here, you can see that I didn't change the way I did it. The only thing is the values changed in my percentages based on how many conductors I had and what my correction factor was. All right. Now, this is something that I want to touch base on also. And we have an illustration for this. Now, this was a change that got made to 210.19A, and they did A1 and A2. This is something everybody's going to have to think about where we're dealing with these branch circuit conductors. And what it says in A, branch circuit conductors shall have an ampacity not less than the larger of the following and comply. Look at this. Well, 110.14C for equipment terminations. Is that where I started?
Yep. Yes, sir.
Okay. Now watch what it says. When a branch,
it seems like this ties in with 210.19 too.
It does. And that's what I'm saying. I'm about to prove everything I said. It says where a branch circuit supplies continuous loads or any combination of continuous or non-continuous loads. So if it's continuous, we take it at 125%. All other loads that are non-continuous, you take it 100%, right? That's basically what A1 is. That's what we always did. Now, let me tell you why this got changed. Because what happened was you would take and do this calculation, and then after the calculation was done, then we would take and apply the adjustment and correction factor to that load that was already there. Well, the 125% was already a percentage that was applied there. So you were actually derating twice. So now they're saying if there's no adjustment or correction factor, A1 is perfectly fine. But
dude, I got some bad news, James. It seems like we created some pretty bad monsters out there. I just gotta laugh, Andrew. That's a good one.
Well, sure it is. Hadn't you heard anything that's into the wiring method just floats magically in air and it's an outlet now? All right. Now, if I look at A2, it says the minimum branch circuit conductor size shall have an ampacity not less than the maximum load to be served after the application of any adjustment or correction factors. Now, let me stop right here. What this means is if I'm calculating all my branch circuit loads and everything are at 100%, okay? And where I take and apply adjustment and correction factors, that'll be based on 100% of the load. There's no 125% added to this, okay? So let's take a look and see what we get here. This might be a little hard to see, but this is the way the illustration is that we have. I couldn't blow it up any bigger. Now, as you look at this, and I would encourage everybody to put this on a bigger screen so you can really see it, but we show you 2 methods here, okay? And we're showing you how to do a calculation where I take a continuous load at 125% and then a non-continuous load at 100% and just size your conductor and overcurrent device. Okay, so
Okay.
in method 1, I'm going to calculate the ampacity. Now, when you go in and you look at our publications, this is what you're going to see. You're going to see these step-by-step calculations with the sections, tables, all the information you need to reference is here. Now, one of the cool things is for the online version, you can actually just hover above, click that section, it'll pull up. So what we like to say is don't just believe everything we say. Look at what we're saying and read the language here, and then this proves what our opinion is on it. All right.
Dude, that illustration's on point, man. That's looking good.
Thank you.
The only thing you're missing is the smoke detectors under the race floor.
Yeah, well, we don't get quite that detailed.
I know,
All right.
I'm just kidding.
Now,
hey, real quick, I got a bone to pick with Andrew. You know that MC is gonna have to be on a GFCI breaker if it's a hidden splice inside the wall. I'm just kidding.
All right. Now, in step 1, if you look at 210.19A1A, you're going to see we have 28 amps. That's continuous. Take it at 125%. That gives you 35 amps. Then I got 12 amps of non-continuous. Take it at 100%. Gives you 12 amps. Add those up. It's 47 amps. I go to table 310.16. The next wire size above that is a number 8, which is good for 50 amps. And the next size overcurrent protection device above that for 240.4B and 240.6A is a 50 amp overcurrent device. Very, very easy calculation to do. Okay.
Oh, yeah.
Now, when I look at method 2, you're going to be looking at 210.19A1B, and then you'll see we got the sections there we want you to look at. But we're going to tell you to take both of those loads now at 100%. So I got 28 amps, 12 amps, add those together. And that's going to give you 40 amps. That's I don't know what I'm thinking here. I'm taking to something else. Then if I look at step 2, then I look at applying derating factors at this point. Well, right up above here, we're telling you that we have 4 current carrying conductors in here. And when you look at the temperature rise here, where is that temperature rise? It says God, I'm having trouble even seeing it. Let me pull it up where I can see it a little better. 106 degrees Fahrenheit. All right. So if I go look at table 310.15 B11, it's going to tell me that's 87%. And then I go look at table 310.15 C1. I've got 80% for the 4 current carrying conductors. I'll take that 40 amps let me rephrase this real quick. What I'm looking at here is I have to take and be able to have a load that's large enough to supply what? The 40 amps.
Oh, yeah.
You see that?
Of course. Yeah.
Now, so in order to do that, if I go over and I look and I say, all right, let's just say I did the calculation on the left-hand side here and I said, all right, I need a 50 amp overcurrent device, and I come across here and I do this calculation. All of a sudden, I can tell you by applying those derating factors, it's going to be less than what? 40 amps. So it's not going to be large enough at that point. So what I had to do is I have to go through here and I've got to look at a conductor that's large enough to supply that. Well, we've already done the calculation for you. And if I go over and I look at a number 6 conductor, it's going to tell you there for THHN, it's good for what? 75 amps. And then I'll apply the derating factors, and that'll give me 52 amps. And that 52 amps is now greater than the 40 amps. So instead of using a number 8, I had to use a number 6 conductor due to what? The derating factors.
Continuous load too.
Well, the continuous load I didn't even do in this calculation. That was in the first one.
Gotcha. Okay.
And
but
that's
could be a factor. Is this ambient?
the ambient temperature that it's in is 106 degrees Fahrenheit.
Gotcha.
So
okay.
that will be at 87%, and that's over in table 310.15B11. Okay. And then you need to look at table 310.16, and then you got to start trying different amperages to make sure once you apply both of those derating factors, the load is large enough than the load that was calculated in step one, which is what? 40 amps.
Yeah, and this brings up a good topic too that I think we've already covered in the myths. So if for some reason that wiring method only travels for 10% of the wiring method in that ambient temperature, you don't have to do any correction at all.
Right. And we actually have an illustration where we show that where it's going, and say you turn up and you go up to an AC unit that's on a rooftop. We show where you have 10 foot or less, and that's not part of having current carrying conductors up there or in an ambient temperature.
Nice.
So we go through, we actually have an illustration, and I can do something on that too eventually, because we have illustrations on pretty much everything. Now,
well, I might have created a monster on this one. We might be here a while.
Well, this is really good here, because what this gets into is looking at 215.2A1. And if you look, they rewrote this section too, and you've got to look at A1 and A2. Well, A1 is just like we looked at when we were looking at 210.19A1A, and then you come over here to A2. What's it talk about? Opacity adjustment and correction factors. See that?
Yeah,
okay. I'm not going to read it all. We're doing.
It also talks about feeder conductors.
That's right. So, yeah, it's not a branch circuit. and when you know, it's like I said last week, when you're going over to feeder, you're going over feeding multiple loads. It's not an individual circuit. It's not for one piece of equipment. That's not what a feeder is. And for people to say that, I'll tell you, every one of our illustrations are wrong, dating back to the 70s, because and nobody's ever said that was a feeder before.
Right.
You know,
dude, I really liked what you said about old man going in there and doing his classes, and the guys that actually wrote it saying that's exactly what we wanted to write it as. That's exactly how we wanted it. We wanted it to say, this is where your starting point is, and this is where your maximum is.
I'll tell you the story. What happened was, you were asking about this. The guy at the time, when they were doing all that work on the motors and everything, the chairman, Dad had done his design book at that time, and he did his motors. And the guy came up to Dad that he was at one of the NFPA meetings when they were going through their code making panel stuff. And he come up to Dad and he said, the way you explain that motor right there, he goes, that is exactly the intent of what we mean by that. And if you look at our publications dating all the way back in the 70s, Dad has always had it where it was the minimum size, next size, and maximum size. And here we go all the way up here. We're in the 2020s. Everybody's agreed with that. Nobody's disagreed. Now you got a few people coming in saying that isn't correct. You know, I'll tell you what that makes me feel like is like basically what you're doing at that point when you say that, and you say he's gone senile and everything, which they've said, which he's not. What that makes me upset about is you're basically saying everybody else that was using these publications, all these engineers, contractors, inspectors, apprenticeships that were using that publication, you're saying every one of them were stupid too, and must be senile, because everybody agreed that was the way that you calculated. And Dad was the first that put it together and put it in an illustrated form with a step-by-step calculation on what was the intent of that the calculation and how it was to be applied. So,
dude, do you remember we had 3 episodes. We had Mark Candles, we had Crystal Hunter, and we had Kevin Muller all hold up the Stall Cup design book as what they learned from.
sure.
On our show live.
And not one of them would disagree with what was said there at the time.
Yeah. That's pretty
Okay.
awesome.
Let's look at a feeder. I'm going to show you. It's the same calculation. I'm not going to spend a lot of time. We're going to show you 2 methods here. What?
Oh, he just said with that open MC splice behind the wall, we could consider a feeder tap.
Yeah.
But he's just joking around.
I tell you, it just amazes me. All right. Now, if you look at method 1, you're going to see in step 1, we show you connected load, and then we show you calculated load. Anything that is continuous, you take at 125%. Anything's non-continuous, you take at 100%. You add them loads up, you come up with 217.5 amps. It's a THHN conductor. I go look at table 310.16. The next size above that is a 4-aught conductor, which is good for 230 amps. Boom, that's it. Just like we would do for a branch circuit. Now, if I look at step 2, look at here. All the loads are taken at 100%, and then I have to look at finding the size that's going to be large enough to protect that calculated load of 193 amps. So looking at this, I've got 4 current carrying conductors. That's it. Okay. There's no temperature or nothing. So now I have to look at a load, or should I say a wire amperage, once I apply the derating factor, that's going to take care of that calculated load. Okay. Well, we already did it for you. It's a 300 kc mill. I go over, look at table 310.16. It's good for 320 amps. Take it at 80%. And that'll give you 256 amps. Okay. Then I went down and then I applied a temperature here to show you. And we're just saying, let's see, what was my temperature here we did for you? 122 degrees. Take it at 122 degrees. Go look at table 310.15B11. That'll give you 82%. Apply that. It's 209.9. That's just right above, about 16 amps above the 193 amp calculated load, and that would be your conductor size. Now, what I'll point out there, did I change my calculation at all between a branch circuit and a feeder? No. The only thing that changed was what? The values. And of course the size, because it is a feeder.
Right.
You know, I'm just amazed that, you know, that if you look at the rules and look at them and apply them and look at the sections that are there and look where it refers you back to, you can see that everything started at the termination and how the terminations connect based on which column I'm going to use between a 60 and 75. And then all you're doing is just looking at what? Your derating factors. I have an adjustment or correction factor. And if I do a branch circuit or a feeder, if I don't have adjustment or correction factors, take the continuous at 125%, non-continuous 100%, you're done. If I have adjustment factors, the only thing you need to remember is that you have to use what is the connected load. And you do not apply any type of adjustment factor to that load. Then you go in and find a conductor that's large enough. Once you apply the adjustment and correction factor for the branch circuit or feeder, make sure it's large enough for what that connected load is, and you're done. Okay?
Right.
All right. Now, this is where we get into some interesting stuff. Now, what you're going to get into here, you're going to go over and look at B211, but this is what you're going to see. They have a little formula. I actually copied this over here. And we actually have it where it's easier to understand. But this is what you're going to look at. And they're going to tell you what is A1. That's your ampacity from the tables. Okay. N is the total number of conductors used to select the adjustment factor. E is the number of current carrying conductors used simultaneously in the raceway or cable, and A2 is the ampacity limit for that current carrying conductor in the raceway. That's where it starts off. A2 equals, and then you have your formula here. Okay. Now,
so is that how they made the table?
Yes, it's based. I'm going to show you here how
Okay.
When you look at this, this is the formula I'm going to use where I have all these different conductors in there. I'm going to show you what they're talking about. Okay, looking at that, you sort of have to know what they're asking you here. Okay, now what happens here is this is the capacity adjustment factors here for more than 3 current carrying conductors in a raceway or cable with what? Load diversity. And you'll look, when I get up above 10 to 24, it'll tell you here, you'll have the double star up there. It'll say these factors include the effects of a load diversity of 50%. Okay. Now let's take a look and see what there's 2 calculations I'm going to show you here. Now, when I look at this, I'm going to tell you here that I have 28 conductors in the raceway that are current carrying. Okay. So,
dude, what did Willie Jackerson wire that? How do you get 28 in there?
Well,
I can only get 24.
I'm just kidding. I know what you're talking about. So if I come back here and I look at 28 conductors, that includes the load diversity of 50%. It tells me I can take it at what percentage? 60%.
Yep.
This is a basic calculation. We have number 12, THHN. I can use the 90-degree C column. That's 30 amps. I had 60% for the 28 conductors in the raceway. Take the 30 amps times 60%. That gives me what? 18 amps. Okay.
Yeah.
Now, when you look at this, it tells you here the ampacity of each one of these is limited to 8 amps. However, only 14 can have this ampacity rating. And that's due to what? The 50% diversity factor. So I'm basically doing what? Cutting that in half, the 28 conductors. You see what I'm saying? That's the basic calculation where you have that 50% diversity factor. All right. Now watch this. Now, when you get in the calculation, I'm going to do the same thing. Now, what I'm going to do here is I've got 28 conductors in the raceway. Okay. Here's my formula up here. All right. Now, as I look at this, we're saying there's a specific amount of current carrying conductors in here. We're telling you we gave you the known values. We're telling you there's 20 of them, and you're using number 12 THHN. All right. So all I'm going to do is take the 0.5. That's the constant for the calculation. I've got my number of current carrying conductors, which is what they were talking about in the formula. That's 28. And then I look at the number that are going to be current carrying in that raceway is 20. I'm going to square root that whole thing right there. That's going to give me 84%. Okay. I still have 28 conductors. So I come back here. I look at 28 conductors. It's good for what? 60%. Okay. Yeah. So I'm going to take here 84% times 60% times 30 amps for the number 12 THHN and the 90-degree C column. And that's going to limit the ampacity for each one of those, or for those 20 number 12 THHN copper conductors to 15.12 amps.
Oh, nice. Dude, now, I'm telling you, it just doesn't pay folks to do stuff like Willie Jackerson. You just don't need to just pack those conduits and do all these complex calculations. You're better off just,
I tell you, that is a lot of information right there. And I've seen a lot of publications. I haven't seen anybody that goes through and shows you exactly how to do the calculation where you're using Annex B.
Yeah, I got it right here.
You worked your ass off to get that in there.
I packed as many as I could.
I remember that episode. That was funny. Oh,
but
all right. Did anybody have any questions on that? I think I covered it pretty intense and thoroughly. So,
yeah, no,
but
everyone seems like
there
pretty happy
are
about
a
it.
couple more calculations in there. I didn't go over because I could be looking at a wire weigh, and I'm looking at 366.22A. I could take where you have 30 or more current carrying conductors, you're over 30, then you got your adjustment and correction factors. I could have thrown that in there, but it's the same principle in the way you apply the calculation. But at least it gives everybody an idea of how to take and apply those adjustment and correction factors and when that 90-degree C column can be applied. I was going to do another one. I just didn't have time to get it all in, but I was going to show one where I had THW in and using the 75-degree C column because that conductor is rated for 75-degree C. Okay.
All right.
And that's
Well,
my topic of the week. Thank you, Bill, for putting that one
all
up
right.
on me.
Nah, awesome. No, I'm glad you got everyone fired up. I learned a lot. There was so many things that I learned that I didn't know. It's really awesome. The stall cups are definitely a leader in the electrical industry as far as theory and everything like that. And I guess we'll move on to the tool review, and everyone will see why I'm wearing a Milwaukee shirt tonight because I am doing a review on Milwaukee. And they came out to the job site and showed us some cool tools.
Like I told you earlier, that shirt should be in red.
I know. Hey, it's
time for tool review of the week. Sponsored by Electricians Only Tool Review and Nipex Tradesman.
So the tool review of the week is the Milwaukee concrete saw. Milwaukee guys came out, dropped it out to the job, and one of the cool things I like about this, for one, they're dropping the two-stroke stuff, which I think makes this a little bit more user-friendly. I was ready to go put batteries in this thing and start firing it up, but one of the things you have to think about is you get that crystalline silica dust, and it has a little port on there. You can see it kind of running out through the whole thing that actually hooks to a water port. I think they have it kind of designated where you could see where it plugs in at, but they have a water thing that goes with this that you can actually plug in. I think the water tank comes in for about like around $150 or something like that. And I could tell that some of my DeWalt buddies are a little disappointed in me for going red this week, but it's all good. I'll take the heat. But I tell you what, I was ready to just take this baby. I was ready to go out and start just cutting drains all over the job site, But the good part about this, which I'm blown away, is that the industry took safety on, and I really like that. That you got a whole crew over there that's going to be using this tool, and they're going to be using water, and they're going to be keeping that silica because, like my boss probably ate about 400 cinder blocks, in his career, and I've probably eaten about 200. So, at least we're trying to get it down to where we're not eating as many cinder blocks as leaders on our crews. And like I say, these tools are not only doing the job that we need to do, which to me, I did not actually test the performance of this tool. I would say the batteries probably suck, but I think they were like a 12 amp hour or maybe a 9 amp hour, but they're a pretty good amp hour. So they should do pretty good for a Milwaukee. You might have to just have one on the charger, one on the saw. But, like I say, overall, I would say I would recommend this tool to anybody out there. And like I say, buy the water tank, and then that way you're not just throwing up a whole bunch of silica dust and, spraying your buddy with a whole bunch of pixie dust.
Cool.
So, yeah, but it was an awesome tool. I had to cover it. It definitely impressed me. I was very impressed. So is there anything else in our Anything else we have up in there? Or you got?
Yeah, you got your question of the week.
Ah,
Let's see what you
snuck
got.
it on in.
All right.
Oh, this is
I'll
a
have
good one.
Color marking on subscribe. That would be C, and I think isn't that like 517.30, 31, somewhere in there?
Yes, sir. Nailed it.
You're
I wanted it
still, brother.
Yeah. I wanted to make a poll out of this, but I knew it'd tip you off on it, and I knew you didn't get a chance to see it, so I wanted to try to squeak one by you. But
You're wearing me out, boy.
Yeah. The thing that's funny about this is that a lot of people think if you just label it on the cover plate, then they're going to remove the cover plate and it won't be identified anymore. But most of the time, a lot of these that to comply with that code are actually red receptacles. So you have a red receptacle with a red cover plate, and then it's identified on there. Right. So that would be compliant either way. But a lot of the codes are a little bit overkill in healthcare. So I might get you.
Didn't they make a change on that, like 2020 or 2017? I think's when that took place.
Yes, sir.
Because I remember it in the code changes. That's why I was like, "Oh, I got this one." He did a code change on me that I actually had in a publication.
I know. I'm probably gonna end up doing a poll on it, just because everyone thinks it's really funny because. I went and I took a class for my NISAT for fire alarm, and they would ask a question, and the first instinct is to guess. Mm-hmm. Like your first instinct isn't go open the code book and see what the code says. Your first instinct is get a guess and get it out there, and then hopefully you're right. Like that was a really good dice roll. I guessed on that really good. But in all actuality, the best bet is to not even say any answer and just go see what the code says.
Yep.
Because in your head, you're thinking common sense. You're like, it's whatever common sense says is right. Nope. It's whatever the code book says.
That's right.
The code book is not common sense. In your head is common sense. The code book is not. But if it says this, then, and your common sense says this, your common sense is wrong. The code book is right. So it's hard to get used to, but you have to deal with that a lot with fire alarm. And to me, it's awesome. I really love it. Like learning new stuff. It's crazy. We ran across a cable we're trying to tone out, and at a certain resistance, we lost the tone.
Yeah.
And I've never seen that before. I've never seen a conductor long enough that you just cannot get signal on it. And I was trying to prove my theory because I was like told the apprentice, I was like, go put your toner on it. Mm-hmm. And I was like, if it's complete, you should have a strong signal going in as you have coming out. And at a certain point, it started getting weaker.
Right.
And I was like, you got an open somewhere. It shouldn't be getting weaker, Mm-hmm. And then I start realizing that tone was starting to hit 100 ohms resistance.
Right.
At 100 ohms resistance, you start losing stuff. So it opened my eyes, but
I'm with you.
I thought it was a parallel open. I was 100% wrong. So.
Hey, I've been out there troubleshooting stuff. I thought damn good and well what I thought it was, and it wasn't. I'm like, what the hell?
I just decided, and it was one of the guys that I work with, one of the foremen. He's like, why don't you just cut the circuit in half? I was like, how do you do that? He's like, just put it to ground. And I'm like, oh, yeah, why are we trying to go through the conductors? Because, yeah, we're doubling the resistance by doing that.
I do that.
Andrew, really, really awesome to have you join us, sir. I appreciate it. He's also a fellow fire alarm ninja. And, yeah, that's cool, man. I appreciate it. He's doing electrical now. But, yeah, I'm back and forth. I've been doing it 27 years. And whatever pays the bills, that's what we're doing,
I do got one question for you, though, I was thinking about. Okay. Have you recuperated yet from the avalanche not still being in the playoffs?
Yeah, probably. It's too soon.
It's still too soon.
The sad part is it looks like Dallas might not be in the playoffs much longer.
I'll tell you, those. I was actually at the pool hall when they gave up those 3 goals. Like real quick, I was like, "You gotta be kidding!" Then they come back tied it. I was like, we'll see how they do. Kraken's got a pretty damn good team. Look like to me.
I predicted that the Stars would just sweep the Kraken, but it is what it is. I mean, it's the playoffs. I mean, look at what Florida did to the Bruins.
Yeah, Boston.
I mean, nobody expected that, and then Florida goes up like 7-2, beats 7-2 on the Leafs. Like nobody expected that either. Yeah. So that's pretty crazy.
Anything can happen during. What do they say on any given Sunday?
Yeah. So I would actually say the number one thing that bothered me the most is I went and I got my Nichushkin playoff shirt, and then Nichushkin leaves the playoffs. You know what I mean? I'm like, oh man, I had my shirt already that he left.
Yeah.
But yeah, what's Andrew saying? Yeah, no, Andrew, you're cool, brother. It's all good, brother.
Oh no, hell no! I like when you give hard time. I think it's funny.
Yeah. Yeah. No. We have like a acronym for a fire alarm guy, and I changed it to fire alarm ninja, and then we try to get like the guys and the gals in there. You just don't want to have all fire alarm guys, so you get the gals in there too, which you could use fire alarm gal as well. But what I changed it to is fire alarm ninja. I changed it in the Urban Dictionary. So,
all you got to do is get Chat GPT or whatever the hell it is. Tell them this is what it means, brother.
Dude, I'm telling you, I have not. It's funny. I have stumped Chat GTP 100% of the time on my code question of the week. So I go do the code question of the week, and then I put it in there, and it'll say the answer, and it'll say, "Oh yeah, you should just do this, and this," Mm-hmm. And so then I'll go in there. I'll say, "Nope, you're wrong. If the answer is C, it could be on either receptacle or the cover plate." And then it's like, well, you should always consult a licensed electrician, But it's just really funny. And Mike, pretty good. A low voltage guy, whatever. Mike knows we've been around the block. We dealt with all this stuff before. Me and Mike, we worked together on projects before, and some of the guys that can make this stuff happen, like. It's funny because they'll be sitting there telling me and Mike like, well, yeah, I hooked it all up and it's not working. You're like, well, did you check resistance? You check voltage? You check? Oh no, I was just spraying and praying. You know what I mean? Like you're like, what? Like you got these meters and stuff for a reason. You can get them up there and you can read them and you can see what they're going. And a lot of guys say, oh, well, I can't troubleshoot anything unless I have power to it. That's a total lie.
That's not true.
You could go up there and you could put your meter on a totally dead circuit. You could tell everything about it.
That's right.
You could tell if it's clear. You could tell if it's reading through a transformer. You could tell if it's hooked to the light. You could tell if it's on, off, different things. So I just encourage a lot of the younger guys to learn how to read your testing equipment. It's your testing equipment is not just a glow stick.
No.
Like if you could read the glow stick, I recommend the AmPro 440. That's what I always use. It's just a glow stick. It doesn't tone. It doesn't do anything. You don't have to turn it on. It just glows. And I like the AmPro 440 because you could put it on a circuit. I might even do it on a tour view and show, but you could actually put on a dimmer and you could watch it dim and go dim and, and no other testers can do that.
Right.
You could actually tell which switch leg is dimming on your dimmer.
That's cool.
And I never seen any that could do anything like that, but that's why I like that. But no, I appreciate you being a good sport, James. You know, a lot of the other guys, you know, yeah, and that's true, Andrew. Yeah, you know, the meter doesn't lie, brother. You know, if you know how to read it. That's the thing. I had one time, and everyone's gonna love this. One of my buddies in one of the groups, we made a meme about this. Like, I got a fluke, so I'm an electrician now, or whatever. But this guy went out and bought this Bluetooth, freaking like the baddest meter you could get, fluke, and he's like, "Oh man, I could read this thing from 20 feet away or whatever, And I was like, "Dude, you don't even know how to read that." He goes, "Oh yeah, I do." He plugs it into an outlet and he goes over there 20 foot away and he goes, "That's 110 volts right there." And I was like, "Dude, that's 110 millivolts. That thing's dead." So it was really funny because that comes into people not being able to. Yeah, and you're right, Andrew. We call them death sticks, but you have to know how to read your stuff. So we really appreciate everyone joining us. Really awesome. I'm gonna go ahead and star that comment for the end of the show. But really awesome to have you guys join in and just blow up the comment section. And it's just awesome that we could do this every week for you guys. And James, thanks for bringing the heat every week. It's pretty awesome. You always have like great topics and just cover them really great and bring up all the cool stuff. So really awesome. Thanks for joining you guys. And I don't know. I'm out of stuff. Are you good, James?
I'm good. I'm tired. I didn't go to bed till real late last night getting everything ready because I have so much going on. You can see I've been yawning. I'm tired. And I haven't even eaten today. I'm freaking starving. So,
well, I really appreciate you, sir. And everyone, remember, make every day an easy day.
Amen. Everybody have a good weekend, and we'll see y'all next Thursday with the great Mark Candells. And he'll have a good topic, and I'll post everything up probably Wednesday or Thursday morning, one of those days, and let everybody know what's going on. Real late.
Yeah,
it's 8:30 here.
Yeah, I know, right?
Peace, everybody. Everybody have a good one.